All right, well, welcome to tutorial number 4 here, where we'll be doing some linear algebra calculations inside of Maya using Python. We'll start out simple here, just with figuring out how to visualize a vector as a line segment. That'll be very useful for the more complex calculations we do later on, just to be able to see how vectors are transformed and where they end up and what they look like. We'll do a scalar vector multiplication. That's pretty straightforward. We'll also figure out how to get object and vertex positions out of Maya using Python code. This will be absolutely essential for doing some more complex and meaningful problem solving inside of Maya. And then we'll finish off with calculating a dot product between two vectors, as well as figuring out how to get normal vectors, right? Using the cross product and getting normal vectors. That as well is another really important operation for loads of stuff we have to do in computer graphics. All right. However, the main point here really is to just get comfortable with performing these basic operations inside of independent functions, so that we have a solid modularized foundation for solving more complex problems, right? You don't want to end up with hundreds of lines of code, all in the same function and with nothing broken out into separate reusable functions. It not only extremely inefficient, but really a mess to read and kind of decipher if someone else has to look at your code later on down the road, or if you're trying to figure out what you did maybe in the past. We always want to have that nice modularized foundation when we're doing this sort of thing. All right, so now with this tutorial, just due to the nature of the calculations we have to perform inside these functions, I know that you're going to want to just hit pause on the video and copy out the function yourself. We're gonna need to make sure we copy stuff over correctly here. So I know there isn't much sense in me kind of like live coding stuff out. It's kind of a waste of video time, right? So I'm going to be pasting in code that I've already prepared. So I'll paste that code in here to this script that we're working on. You can go ahead and hit pause, make sure you get everything copied down correctly, and then we'll go through and just quickly discuss the formulas so that we clearly understand what every line of code is doing, and we'll see the results. All right, so let's get started here with a very simple and straightforward operation. Let's figure out how to actually visualize a vector as a line segment. So I'm going to start out here with let's just create a variable called vector, and let's store a list of values, and let's actually store the vector pointing. How about +1 down the z-axis, right? In my Maya viewport here, I'm always taking a look at this set of axes down on the bottom left-hand corner of the perspective viewport here, just so that I keep track of which direction my axes are pointing, right? So I can see that my positive z-axis is pointing this direction. So I know where this vector should land, right? When I type in here 0, 0, and 1, I know where I'm expecting to see this vector be drawn, right? So there's our vector. Now, how do we visualize this? All right, so a pretty straightforward method of visualizing lines, vectors or line segments or anything like that inside of Maya is to use the curve command, and this actually creates a NURBS curve. Now, quite specifically here, we are going to be using a degree 1 NURBS curve. And if you recall from our video on NURBS, or actually on Bezier curves as well as NURBS curves, the same sort of idea exists for both types of curve objects. You'll recall that a degree 1 curve basically gives you a polyline, right? There's no actual curvature in the object itself. It's just, straight line segments connected to each other. So we will be using a degree 1 curve for this object. All right, so I've pasted in this function definition here. You can go ahead and hit pause, make sure everything is copied out here, and I will make sure that I have the text editor zoomed in enough here so you can clearly see everything that needs to be copied down. All right, so assuming you've had a chance to get this all copied down into Maya for your own use, let's just quickly talk through what is happening here before we run this. All right, so we are defining a new function here called drawLine, and we'll accept the parameters start and end. We will eventually use these as lists, essentially as vectors, just giving us a starting position and an ending position for this line segment. So we do need to keep that in mind and pass the correct information as arguments to this function call when we do eventually call it. And let's jump inside and take a look at the single line of code that we're running here. We will be running a cmds.curve, right, which just creates a NURBS curve object. And this P, it stands for position, and it basically just defines the start point and the end point of this curve. You can see that, and actually if I remove these two tuples inside of this P argument here, we can see that it's really just accepting a list of two values, and those two values being two tuples. So inside this first tuple here, we just pass in the x, y, z coordinates of the starting point, and then for this second tuple here that we are defining for this list, we're just specifying that the end position of this line segment is going to be, well, really a vector addition from the starting position to the end position, right? So otherwise, if we did not have this start value here, we'd basically get vectors drawn from our specified starting position to an absolute coordinate, an absolute world space coordinate for the endpoint here, right? So if my vector was 0, 0, 1, and if I started that vector at an arbitrary point in space and then drew it so that it ended up on the endpoint 0, 0, 1, well, we'd have a line segment just drawing to the absolute coordinate of 0, 0, 1, which is like right here in 3D space. So we do want to make sure that this vector is being drawn from the starting point to the end point. All right, so there is the definition there. Let's go ahead and run this function. Actually, let's just make a few sections here in the script. So these are going to be our function definitions. Put our variables up here. Put our function calls down here. All right, so let's do a draw line. Let's draw a line from origin. Let's start off just by drawing a line from origin. Right, so that'll be the first argument I pass in to draw a line, right, to give me my starting point at origin, and my ending point will be at vector. All right, there we go. Let's go ahead and run that code, and there we have it. All right, so we have a vector being drawn from origin. Let's go to curve points here, or sorry, let's actually go to control vertices, so we have a point being drawn from origin to the location specified by this vector. Let's try this again. Let's just undo here so we get rid of this curve object. Let's draw a different vector. Actually, I'll call this function a second time, and let's draw a vector from, how about, I don't know, 1, maybe 1, 1, 1. to 0, 0, 1 from the starting point. All right, so now understand the way we're setting this up, because it's the way that vector visualization will be most useful to us in the future is to, again, draw that line segment, draw that vector as starting from a defined position in space. So we're getting the line segment drawn 1 unit in the z-axis, starting from the point 1, 1, 1. And there it is. We can see that. Starting from 1, 1, 1. Right, that point right there, drawing 1 unit in the z-axis. All right, pretty straightforward. Let's get rid of those lines, and we can also get rid of those those function calls there. And let's tackle our second function here, which is going to be for doing a scalar multiplication of a vector. All right, so let's get that one in here. Let's put this one right down here, scalar multiply. Let's zoom in here so you can hit pause and copy this function out. And provided you've had an opportunity to do that, let's just quickly talk about what's happening here. Again, very straightforward. We're just accepting a vector, and so just a single variable, which is going to be a list, a vector value, and then a second parameter, which is going to be just a scalar value here. And then we just go through we go through for each vector component and just multiply that by the scalar, returning the result. All right, so let's see this in action here. Let's do a draw line again, actually. I should have kept this up from before. So let's do another draw line from origin to vector. Right, we know what that's going to look like. However, let's just bring that back up. However, let's scale this vector. What did I call it? Scalar multiply. I called it scalar multiply. Right, so we're going to perform a scalar multiplication on this vector, and we know the order we have to pass in these arguments here. Right, first is going to be the vector that we are scaling. The second value is going to be the scalar that we are using to multiply it by. All right, so let's go ahead and run that. So we can see in this case, we are drawing a line from origin to vector times the scalar 2. Right, so every component has been multiplied by 2, and there we have it, right? We can see that line segment extending out to z equals 2, right? And this works for any value, right? Maybe let's put a 2.5 in there. Right, so there is a vector scalar multiplication function. Very useful for if we have an arbitrary vector in space, we want to scale that up to see where the vector lands, as it extends out into the scene. Very useful for that purpose. All right, now the next one we're going to do here is for getting object positions. Again, we're going to have to do this very frequently when doing linear algebra problem solving inside of Maya. We are going to have to get object positions quite frequently, right? So, in fact, what I'm going to do is I'm going to create a locator. Let's just leave that locator at origin so far, and we will be querying essentially for this object position. Now, in order to do that, let's define another function here. Let's call it getObjectWorldTranslation, because again, we're just going to be looking for the position here. We're not going to be looking for any other transformation attributes. But yeah, let's zoom in here so that you can get a chance to copy this one out. Again, just another single line function definition here. But provided you've had a chance to get that copied out, let's take a look and see what's actually happening here. So all we're doing is accepting really the name of an object, all right? So this is going to be the name of the object as specified in Maya's scene graph. So that the name of the transform node, so in this case, it'll be just locator1. We will in just 1 second be passing the string locator1 into this function call here, into the call for get object world translation. And then once we do that, we're going to be running the xform command. Now we will be using the xform command a bit later on to do actually many different operations. It's a very useful and versatile API call here. It has loads of different functionality, but in this case, we are doing a query on the object specified here in the object parameter. We are going to be looking for the object's world space translation, and this is by setting rotate pivot equal to true. This is actually just a really efficient way of just straight up getting the object's actual position in world space, regardless of whether or not it has transformations applied to it. All right, so, and just to be clear here, the value that we are going to be returning out of this function is going to be the position of the object's origin, right? So wherever the object, or I should say the object's pivot, right? It's the origin of the object's local coordinate space. However, in 3D graphics terms, we call that the pivot of the object, right? So wherever this pivot happens to be, that is the value we are going to be getting, right? So if we're assuming that pivot is at the center of the object, then we're going to have to make sure that's true, right? So a number of different things to keep in mind here. So let's make use of this get object world translation. I'm going to do a print, and we're going to be printing the results of this function. We're going to be printing its return value. And so what will it be returning us? It'll be printing the world space position of whatever object we pass in as an argument here. So like I said, we are going to be querying for locator1's position. So let's just pass that in as a string value. All right, so there it is. Let me zoom in on the console here so we can see this nice and clearly. There it is. There is the printout in the console here telling us that currently the locator is at origin. Let's do a translation on this, right? So just pick an arbitrary translation here. Go ahead and run this line of this function call again, and we can see that now locator1 is positioned at negative 1.83. Essentially on the x-axis, right? 2.28, 2.27, 2.28, right? On the y-axis, I guess I should round to 3 decimal places here, since that's what we're getting in the channel box, and negative 0.259, right? Negative 0.259 on the z-axis. So this function we can use to get objects' world space transformations. All right, and I mean, even already we can start to do some fun stuff with this, right? What if, let's remove the print just for a second. What if we wanted to draw a line from, hey, let's pick origin again, so 0, 0, 0. What if we wanted to draw a line from origin to the position of this object? All right, well, we can just pass in basically the return value of this function call to the draw line function. Go ahead and run that again, and we can see that now we are drawing a line right from origin to that object's position. All right, so hey, I'd encourage you, either at certain points along the way here in this tutorial, or once we're all done with these basic linear algebra operations, go have some fun with it, right? Start putting things together and see like, what lines you can draw, what information you can figure out about the scene. And that'll definitely help with retaining this information and figuring out in the future all the different things we can do with it. All right, so there is getting world space translations. All right, now the next thing we're going to need to do here is to get individual vertex positions. All right, so we figured out how to get the position of an entire object, but obviously polygon objects are built of geometry involving lots of different vertices. There's lots of different linear algebra operations we're going to need to do involving those vertex locations. So we're going to need a way to get the XYZ coordinates of individual vertices. Now, let me get this function definition in here. This is going to be considerably longer. There's a number of things we have to do here. So let me get that on the screen, and I can zoom in this amount. So you can go ahead and copy that one down. Now there are a number of different ways of implementing this function, but what we're going to see here is that I'm going to be accepting the name of a particular object as well as a face ID. All right, so in fact, let's just get a little bit of intuition on how that works. Again, a bit of review from back in the video when we talked about how geometry is stored by your 3D software. Let's go ahead and create a cube object, and as well under display here, we're going to go down to polygons and turn on face component IDs. All right, so we can see here that Maya has a certain, it's basically an index in a list of values. All right, so each face here has an index associated with it. So by specifying the name of this object, it is going to be pcube1, and the number of a particular face will be able to access information about this face itself. All right, so now this is the way I've chosen to implement this function, just to prepare us for something we're going to do in the next tutorial, in which case we are going to need to get all the vertex locations that belong to a certain face, right? You could implement this function to just get you one vertex location, and that'd be totally fine too. But I've decided to do it this way just to help us out in the future when we're going to have to get vertex positions. All right, so in essence, this function is going to get all the vertex positions that belong to a given face. So let's start by just running this function on face number 0 of this cube, just to see how it works. So we will understand we are returning a list of lists. Actually, the vertex A, B, C, and D will be lists. So let's just keep that in mind here. We'll print get vertices, and let's pass in the name of this object. Again, it will be pcube1, as well as the face we are targeting. So that is face 0. Let's go ahead and call that function. All right, so right off the bat here, let's just open up our channel box so that we can see some information about this object. Right off the bat here, we can see that these results do make sense, right? So we're talking about this vertex, this one, and this one. And we can see that the world space translations of those vertices are as follows here. So we've got one at -0.5, -0.5, and positive 0.5. So let's figure out which vertex that happened to be, right? So negative 0.5 on the x, negative 0.5 on the y, and positive 0.5 on the z, right? So that would be this vertex right down here. And we could do it for one other here. Let's look at 0.5 on the x, right? So that would put us on this side over here. Negative 0.5 on the y, so we are beneath the xz plane. And again, another positive 0.5 on the z, so that would be this vertex right here. And if, in fact, we can prove this to ourselves just by, let's turn off face IDs and let's turn on vertex IDs, right? So we just said, well, actually, we were just selecting them a minute ago there, right? We said the first one was vertex 0 here. The second was vertex 1. And yeah, that makes complete sense, right? Those were the first two vertices that we looked at there. The components match up, or the position components match up, so that we can see that this is indeed working properly. Let's go back and let's actually turn off component IDs. We want to keep our workspace nice and clean here. All right, but before we move on, I do just want to go through this function and make sure that we all understand what it's actually doing, because, well, Maya can be a little bit difficult to understand, or the Python API can be a little bit hard to understand sometimes. So let's just make sure we understand what's happening here. And the way I'm going to do that is let's actually remove the print for the return value of get vertices, and instead let's just print out individual values as we go here. So for starters, we're going to print out the result of doing this PolyInfo API call. All right, so we do a PolyInfo call here. What we're looking for is the IDs of the vertices associated with a given face. So yeah, we call PolyInfo. The first argument we pass in here is just a string. This looks a little bit complex because we are doing some string formatting inside of Maya, or inside of Python, I should say. But really, all we're doing here is we're just populating this first, basically interpolation with the name of the object that we're talking about, right? So object name gets substituted in here, and the face ID gets substituted in here. So really what we're not doing a concatenation, really. We're interpolating some expressions here and substituting in some new values into this string. Really, the string that we're constructing here is, well, it'll be p^1, right? That's the name of the object, dot f, and then square brackets, right? And then we substitute in the face ID. So that is a string that we are creating with this format, with this string formatting right here. All right, no big deal. And then we just pass in another argument here saying that we're trying to get the vertices from a given face. We just set face to vertex equal to true. And the results here is this very strange looking list where we have this. It honestly is rather strange that Maya gives us information this way. I'm not quite sure why it's formatted in this kind of difficult to use manner, but we can work with it, right? Python is great at list manipulation and string manipulation. So in fact, that is the next thing we go right ahead and do, right? So the next thing we do here is to do a split on this variable vertex IDs converted to a string. So let's now print out the value of this vertex IDs. So now we have we do have a list within a list However, we can see that this list now contains individual elements where starting right around here, right? So 0, 1, 2, starting at index 2 and going on 3, 4, and 5. Those indeed will be the vertex IDs that we are looking to get their positions, right? So those are the vertex IDs we are targeting. Let's get rid of that print call there, right? And so now we move on to actually getting the vertex positions in world space, right? So you'll see that we do use an X form again for this, right? A very, very useful function call here. We can use it for getting vertex information as well. So for vertex A, right, it's going to be the same operation for each vertex. For vertex A, we begin again by doing a string format. We're just constructing the same sort of type of string here. It's going to be the object name dot VTX open square bracket, and then we just pop in the vertex ID, right? So again, remember, vertex IDs 0, 1, and starting at index 2. It's kind of strange and difficult to wrap our minds around. Why on earth do we have this other kind of useless information here? But starting at index 2 of this list, we get the first vertex ID we are interested in. So we substitute that in. Again, it's going to be a query. We're querying for the vertex translation, and we're looking for that value in world space. Right, so the same thing happens here for A, B, and C. And actually, just before we move on to vertex D, let's just make sure we have an intuition for how this works. Vertex A, let's print that out. And so there it is, right? So there's our neatly formatted XYZ coordinates of the position of vertex A in world space. Get rid of that. And let's just talk about vertex D for a second here. The reason we start vertex D off as an empty list, and then we perform a check to see if this vertex IDs, if its length is 7, well, then that means there were 4 vertex. And in fact, I should pull this up again just so we can understand what's happening here. It is a bit difficult to understand, right? So 1, 2, 3, 4, 5, 6, 7, including this last bit right here, right? So that makes for 7 elements in this list. If there are 7 elements in total, then that means there is a 4th vertex, a vertex D, right? That is the 4th vertex of a quad polygon. If, on the other hand, this face was a triangle, then we would only have 3 vertices listed in here, and the length of this list would be 6, right? So basically, we don't want to be trying to access information that's not there, right? That would give us an error if we tried to access a list element that did not exist. Therefore, only if the length of this list is 7 do we actually go and query for the position of that final vertex ID 5 there, right? So again, we'd have to scroll back here, but yeah, so ID number 5, or sorry, element 5 of the list vertex IDs contains the ID for that 4th vertex. And then when we're all done, well, we just return a new list with all of those elements. And it's okay if the 4th vertex basically is just an empty list here. We will later on, when we use this vertex position information, we'll intelligently parse it so that we know that, well, if we only have 3 values here, then we're dealing with a triangle. If we have another value here, well, then we have a quad, right? But we just want all the information returned to us. All right, so that is how that function works. The next thing we'll go ahead and do is figure out how to calculate that dot product All right, so we can get rid of this object for the time being. Let's get rid of that call. And let's get in a new function definition here. This one's going to be another single line definition. Let's make some more space here so that this is a little bit easier to read. And let's zoom in nice and close. All right, so here is a function for getting the dot product between two vectors. So again, provided you've paused and had a chance to write this one out, let's just take a quick look at it. So we're going to be accepting two vector values here, right? Vector A and vector B. And then we're just doing the cross product, a three-dimensional cross product on those values. So that's the x value of A times the x of B plus y of A times y of B plus z of A times z of B. We sum the results here and return that value. So let's quickly just visualize again what we're getting here with the dot product. Of course, we've way back at the beginning, we had our video which went through dot products and just discussed the visual intuition behind what this scalar value actually is that we are getting when it comes to dot products. But let's just do that again. Run the code using two different vectors and see how this works inside of some 3D space, right? Where it's a little bit more interactive. So we already have one vector here. In fact, I'm just going to call this, just to keep them separate, actually, I'll call this one vector A. We already know. Let's actually draw it, actually. Yet again, I should have kept this function call in here. Draw a line from origin. Well, that needs to be in a list, right? All right, so we're going to draw a line from origin to vector A. All right, so there is the first vector we have. Let's also define vector B, and let's make this one pointing in a similar direction to vector A. So, well, if we draw it maybe from origin to, let's see, that'll be -1 on the x-axis. So from origin to -1 on the x-axis, let's keep it flat, just on the xz plane. So 0 on the y, and again a +1 on the z-axis will cause this vector to be drawn. Let's go ahead and put it in here. Draw vector B. And actually, before I get too many lines drawn on top of each other, let's just delete those and do it again. Drawing vector A and vector B, and there we go. All right, so there's vector A and vector B, and maybe let's turn off the grid so that we can see these nice and clearly. All right, well, we already know that we should be getting a positive dot product here, a positive scalar value, because these vectors are pointing in the same general direction here. Well, let's go ahead and calculate it, all right, and print the results. All right, so again, with the dot product, we are just returning this new scalar value, so we will have to print the results here. Put in that function call and get the dot product between vector A and vector B. And let's delete those vectors, run the whole script again. And there we have it. We have a positive value of 1. That makes perfect sense, right? We're getting a positive value here, indicating that these vectors are pointing in a similar direction, right? Let's just try a few other values here. Let's bring that grid back. If we put this maybe at, I don't know, negative 0.5 on the x-axis, it'll be a bit of a tighter angle between the two vectors here. Still getting a value of 1, right? Of course, if we visualize the projection of of vector B onto vector A, it does make sense. It covers the entire length of vector A, right? So maybe let's put this one 2 units in the z-axis. Let's have some fun with this and just, again, develop. I'm all about that visual intuition, right? Let's make sure we can clearly visualize what the dot product actually means. So here we go. Again, if we imagine that projection from vector B onto vector A, well, yeah, it covers twice the distance, right? Twice the magnitude, if you will, of vector A, right? So that does make perfect sense. But again, if all we're interested in is what direction are the vectors pointing, well, any positive value here means they are, generally speaking, pointing in the same direction. Let's change things up a little bit, moving away from the positive results. Let's get a perpendicular vector here. So we're going to go, let's take a look at our coordinates down here. Let's go, maybe let's go +1 in the x-axis. Let's go +1 in the x-axis here, 0 in the z-axis. So makes perfect sense. Makes perfect sense that these vectors are indeed perpendicular to each other. Again, we can verify that just by looking at the grid here. You can see that there is a 90-degree angle between those. And well, what is the dot product? Well, we already know from our video on dot products that the dot product of perpendicular vectors is precisely 0. Again, the projection of vector B onto vector A covers 0 the distance of covered by vector A, right? So I think we lost that in the console, so let's run that again. There it is. There's our value of 0. There's our dot product. Makes sense. Let's do one more test here, bringing the vector B pointing in the opposite direction of vector A. So we'll have to use a negative z value here. Let's do a -1 on the z-axis, and I mean, sure, let's do 1, 0, -1 for vector B. So again, hide the grid. Here we go. 2 vectors pointing in opposite directions, and well, again, makes perfect sense. We do have a negative value here, a negative dot product, which implies that the vectors are pointing in opposite directions. All right, so there's our dot product function call, and let's move on here and do one last thing. Let's figure out how to calculate the normal vector, and we're going to see that this operation requires a number of other operations as well, right? So we're gonna need to actually bring in a number of additional functions here to finally calculate the normal vector. All right, so get ready for quite a bit of typing here. In order to figure out the normal vector of a polygon, we are going to need a number of other components. All right, so this is going to be one function call after another. Here we are zoomed in nice and close to this new getNormalvector function, so I'll give you a chance to get through this one. But I'm actually going to wait for the description of what is happening inside this function. I'm going to wait for that until we get the rest of the required functions written out, because, well, we're going to see that, the very first line of getNormalvector is going to require talking about a different function. So we got to do stuff in the correct order here and get all our dependencies in. All right, so provided you've had a chance to get this one written out, let's go ahead and let's put get cross product right above here. So there is our get cross product. All right, so this is the new function here. Go ahead and hit pause and copy this one out. A bit tedious, but it's got to be done. Hey, at least once this is written out in Python code, then you have it ready to go, and you don't have to reproduce this for future tutorials, right? Hang on to this script. In fact, that is a good reminder to me as well to save my file so that you have this ready to go for the future. And once we have that, we'll want to also have a calculation for getting our vector magnitude. So again, I'm going to make some new space above get cross product and put in get vector magnitude. So you can go ahead and hit pause and write that one out. We're also going to need a get or a vector from points. All right, you can name this one what you want, but we will need to be able to get a vector from arbitrary points in space. So just one final function here, which we'll actually need in order to calculate the normal vector. All right, so let's put it all on one screen here. This is all of our new code. Again, a bit tedious to write that all out, but once you have that all finished, let's go ahead and discuss what is happening here. All right, so well, we know what a normal vector is, and in fact, let's visualize one just quickly here so that we have something to point to as we wave our hands around and discuss this. So here is just an object, and well, if we want to visualize the normal vector of a certain polygon here, say for example polygon 0, just to keep this easy, right? We know that polygon 0 is right here. There's this guy right here. Let's turn off the grid and go ahead and try to do this. So we're going to need to get normal vector. We're going to need to pass in the vertices of a triangle. All right, so let's take this one step further and think through what we actually need to pass in here. Well, we already have a function for getting all the vertices of a particular face, so we can use that. All right, so get vertices of, and then we know we need to pass in the object name as well as the face ID here. So again, the object name is pcube1. And we're going to be talking about face 0, that is that polygon right there. And we just have to watch this, though, that we give this the right information. So again, get normal vector expects 3 vertices. And in fact, let's just remind ourselves what get vertices is actually doing here. It is giving us a list with 4 vertices in it, right? But we only want to be calculating the normal vector on a triangle, right? A polygon that is guaranteed to be flat, all vertices coplanar. So in fact, what we're going to do here is let's do it this way, just so it's nice and clear. Say triangle vertices is equal to get vertices pcube1 face 0, and then let's pass in the 3 vertices that we're interested in here, right? We want to specifically get the normal vector of the triangle specified or represented by vertices A, or the first one, A, B, and C, right? The first 3 vertices. Let's just put that in here. All right, so again, this triangle vertices variable is a list. It'll have 4 sets of vertex positions. We're only going to be passing in the first 3 positions relating to the first 3 vertices of that polygon. If we need to get the normal vector of the other triangle represented in this quad polygon, we're going to have to do that for the other set of vertices, right? So this is only for the triangle ABC. Okay, so there it is. Let's run that. Let's print the results. Print the results. And well, I made a mistake here. Get normal vector takes only one argument, 3 given. Of course, triangle vertices expects those vertex positions as a single list, and I forgot that, and I passed in 3 values here. So I'm just going to wrap those 3 values in square brackets to turn that into a list. All right, so just right off the bat here, we can see this is already working. Our normal vector of the triangle ABC, well, we know that both triangles have the same normal vector here. This polygon definitely is flat. But the normal vector of the triangle will be 0, 0, and a 1, a positive 1 on the z-axis. Well, let's take a look. We know our positive z-axis is pointing in this direction, and so that makes perfect sense, right? The calculation is working properly. In fact, let's just visualize it. Let's just visualize it using draw line. So what we're going to do here is, I guess we're going to have to do a draw line, and as our starting point, right? Because remember, draw line does use a starting point. I guess we can use one of the vertex positions. Let's use the position of vertex A as that starting point. All right, so that will be the starting point, and the end point will be, well, the position or the end position specified by this normal vector. So let's just actually cut and paste that entire function call. Sorry, it is a long line of code here, but let's paste that entire getNormalVector function call into this this draw line call. All right, so there's that. All right, and oh, I made another mistake here and did 2 things actually. One, I forgot my closing parentheses here for the draw line call, and I also had this extra square bracket here. It was just a copy paste error, so do take care when doing that. So when we run this, we can see that we're visualizing our normal vector here. Again, it's a unit vector pointing positive 1 on the z-axis. And we are drawing that from vertex A of the triangle in question. All right, so that was a bit long-winded there, just to get a visualization of what we're talking about here with the normal vector. But now that we can see the results, let's go ahead and just talk through what these functions are actually doing. All right, so starting with the function getNormalVector that we're actually calling here. What is it doing? All right, so, well, we already know because we had to call it, right? So it accepts a single list with 3 vertex positions inside. And then the first thing we go ahead and do is construct 2 vectors out of those vertex positions, right? We know that we're going to need to do the cross product here to get that perpendicular vector from 2 other vectors, or the new vector perpendicular to the original 2 vectors. So we do have to construct vector A and vector B. This is where the vector from points function comes in. So we pass in the first and second vertices here, or in other words, vertices A and B. All right, so let's take a look at vector from points. That is right up here. Zoom in a little bit. That is right up here. All right, so vector from points takes 2 points in space. Of course, we know these to be the 2 vertices that we're currently working with, and it just returns a vector specified by point B, the x components of B minus A, the y of B minus A, and the z of B minus A, right? So just taking the differences between the pairs of components, we get a vector from vertices A and B, right? From A to B. And then we go ahead and do the same for vector B here. However, do note that you do want to make sure that vertex, doesn't matter what it is, but you got to have a common base for these two vertices. So just make sure the starting point of both vectors is the same vertex. So I picked vertex A just to keep it simple. So understand these vectors are, I should probably have a comment here. This is vector AB as well as vector AC, right? So vector B is the vector from vertex, the first vertex to the third vertex, right? So AB and AC. Next, we go ahead and calculate the cross product, all right? So just breaking everything out into separate lines here. The next stage is to get the cross product between vector A and vector B. Let's take a look at that function, which is right up here. All right, we're accepting A and B as parameters here. Let's start out with a cross product of just the zero vector and go ahead and do the calculation. Right, so the x component of the cross product will involve the y and the z components, right? The y and the z components of the vectors, right? We can remember that handy little trick when calculating the cross product, right? The y involves the z and x components. It involves the other components compared to the component that we are currently calculating. So you can review the formula for calculating the cross product if you need to, but that's what we have implemented here. And then we just return that list containing the components of that new perpendicular vector. Right, so that's what we have here. Remember, this is the non-normalized cross product. It is not a unit vector. So the final step we need to do here is normalize that cross product. And so, I mean, actually, I just realized here that when I had written this before, I never actually stored the normal vector before just returning it. So this zero vector here is actually unused. So sorry about that. I forgot what I was doing when I prepped this. But what we do is we first need to calculate the magnitude of the cross product. Again, just taking a quick peek up here to the get vector magnitude function, right? We take in a vector and calculate, Pythagorean theorem, essentially, right? So take the x component squared, the y component squared, and the z component squared. Of course, the double asterisk operator here in Python being for doing exponents, and then of course taking the power of 0.5 to get the square root of the result here, right? So just returning the square root of that gives us the magnitude of the cross product. And then, like I said, I didn't actually store the normal vector before returning it. You could do that, create a zero vector perhaps, and then just assign the normal vector to that value if you needed to use it for anything else inside this function. However, we don't need to do that, right? All we need to do is just return the normal vector itself, which is the components of the cross product divided, each of them divided by the magnitude, giving us that unit vector, right? That unit vector, which is our normal vector here. All right, so hopefully that was useful. Just taking a look through these pretty fundamental calculations for linear algebra, and just running a few of them inside of Maya here, and building on that visual intuition for what these calculations actually give us, because that is the key skill set to walk away from these videos with. We want to understand intuitively what happens in 3D space when we perform these calculations, and how we can use the calculations to solve problems. All right, so good luck with maybe experimenting around with these functions that we've written here, and we'll be building on this in the next tutorial.